Okay, this paper basically that I'm like presenting now is based on large planets may not form fractionally large moons. So Miki Nakajima is the first author and the corresponding author. So she is. So I'll just give a little description about her. So she's an assistant professor in the University of Rochester. So here we can see that her educational profile. So she did her BSc from Tokyo Institute of Technology and also MSc from there, and from uh, California Institute of Technology she did her PhD, and currently she is working as an assistant professor in University of Rochester. So there have been a lot of interest about the formation of the moon. One of and uh, Because of the influence of moon on the earth itself, because of the tidal effects, and the whole axis of the earth is also controlled by position of the moon and its velocity. So based on due to several other reasons, formation of moon is of quite interest to people, and a large number of models have been proposed. So the one of the most common model proposed is the canonical model that suggests that a Mars-sized uh, uh, impactor, it collided with the Earth and created a dust ring around the Earth, and from which the later accretion gave rise to the moon. So this is the giant impact simulation, and this theory is supported by various evidences such as moon's mass, the iron depletion of moon, and angular momentum of the earth moon system. So these are the pros that support this particular model. However, there are some problem with this model as well, that is which is like the isotopic composition of earth and moon, they are quite similar. For example, oxygen, silicon, tungsten, these isotopic composition of earth and moon are almost identical. Now in case of a impact like this kind of giant impact, uh, uh, cases of giant impact, the most of the disk material from which the moon possibly accreted is mainly derived from the impactor itself. So therefore the contribution of earth will be less compared to the impactor. So that is a problem with this particular theory. So there have been other alternative theories as well. So one is that the collision of two half Earth-size objects, and or some high energy and high angular momentum cases. So in this case, what will happen is more interaction between the impactor and the Earth, proto-Earth-like body will occur, and as a result, even like even the mantle will come in contact, like it will participate in the like total impact process. However, in this theory, the problem is that the final angular momentum of the system will be about 2 to 3 times higher than the current value, and which cannot be easily removed from the system. And also, based on this, it is not easy to explain the exact identical isotopic ratio. So another theory that is proposed by people is that multiple impacts occur. So small impacts at smaller scale impacts with Earth and other impactor bodies occur, and as a result, multiple times material is supplied into the accretionary disk, and therefore the in that case, but even in this case, the problem is that the moon would still hold isotopic signature that originates from the impactor itself, and contribution of the earth from the earth will be less. So these are the current models that uh, exist at the present. Also, another thing that is essential to understand is the vapor mass fraction. So in case of these three models, what will be the vapor mass fraction? So what is the vapor mass fraction in this accretionary disk? The amount of vapor compared to liquid or solid particle. So if the impact are of high energy level, that is in case of energetic impacts, the VMF is generally of a higher value. For example, in canonical model where the energy is low, the VMF value is about 0.1 to 0.3, and it increases most in case of the high velocity and high angular momentum case. So that the value ranges from about 0.7 to 1. So as the disk gradually cools, the VMF decreases because gradually with the decrease in temperature, the liquid they accretes and they form larger particles. And as a result, this amount of total VMF decreases. And this amount of VMF, it also has a very important role in the formation of the moonlet, small moons. So these kind of planetary collision that has been explained is very common in any young solar system, and therefore we can expect the presence of impact induced moon in other solar systems as well. However, the Kepler mission and the follow-up study with the Hubble Space Telescope, in all of these studies, no exomoon has been confirmed to date. So one of the objective of this study is also to find out why this exomoon formation is so rare and how we can pinpoint where to look for. So discussing the objective of this study has the main objective to constrain the condition of formation of impact induced moons, and to constrain the lunar origin, and to explain the lack of confirmed exomoons to date, like why are we not finding exomoons in these missions. So what approach they have used? They have used impact simulations with the smooth particle hydrodynamics, which is the SPH method. And here they consider fluid as a collection of particles, and they follow the like they create the mesh system and follow the Lagrangian principle. So I am not very clear about this particular method. Maybe later we can discuss. So for using this particular method, what they have considered is two n-member planetary composition has been taken. So first is a rocky planet where they have considered 70% of forsterite mantle and 30% of iron core. And the second type of composition that they have taken is an icy planet type of composition, where they have 70% of water ice and 30% of forsterite core. So they have not really dealt with the gas giants or mini Neptunes, because that was not the primary focus of this study. So initially they considered the gas drag, which is a very important or controlling factor for formation of these moonlets. And I would like to mention that this is the first study where they have considered the equation of gas drag or radial fall of moonlets into their study. So this is the particular equation and the method they have used. So I cannot go into details of this because I am not very sure of this method. So I'll discuss the procedure and the implication. So generally, when the accretion rate disk accretes or it gradually cools down, the small liquid droplets, they gradually become spores. And because in case of a high VMF accretionary disk, the velocity of this vapor phase is very slow or low compared to the liquid or the solid part. Therefore, in normal case, the liquid droplets would have had a higher velocity, but due to the presence of this large amount of vapor, their velocity is decreased, and this is known as the gas drag. And as a result, they fall onto the planet within a short time scale, and therefore they cannot grow further. So this is a problem of formation of the moonlets, and they generally cannot increase in size much when the amount of VMF is very high. Therefore, if the amount of VMF is low, it is easier to form moonlets, because in that case, the concentration of the liquid and the solid part will be higher and they can easily accrete. And an initial vapor-rich disk, it can start forming stable moonlets once the system cools down and the amount of VMS, it decreases. But by that time, a significant part of the disk mass will be lost, and therefore no large moon can be formed, and the moonlets that will be formed will be very small in size. So in case of this SPH simulation setting, they have considered some of the parameters. I'll show the table later. And so they have used the pressure graduate parameter to characterize the strength of the gas drag. And if we think about high VMF system, so in case of a rocky planet, the disk will be made of silicate vapor and a small amount of liquid. So this is a high VMF condition. So most of the disk material will be silicate vapor, and the magma or liquid will be less in amount. In case of an icy planet, the most bulk composition of the accretionary disk will be stream disk, will be stream and steam, and the lesser amount will be the silicate droplets. So these are the parameters that have been used for the particular model. So what they have considered is, this is the ratio of the total mass of the system divided by the mass of the Earth. So this is the mass of the Earth. This is the ratio between the mass of the impactor and the proto-Earth kind of body. This is the velocity, and they have taken a constant angle, which is which is 48.5 degree. So the impact angle is 48.5 degree, and these are the VMF condition, and the velocity is basically the escape velocity for this particular setting. So using these parameters, they have first they have considered it for the rocky kind of planets. So these are the rocky planets, and for the ice planets, they have run the model again separately. So if we look at the result, these are the two. This is the figure which shows that how the cooling of the accretionary disk occur in case of a rocky planet and in case of the icy planet. So mostly, if we look at the initial figures, what we see is the dynamics of both the system is quite same. However, at the final stage, we do have a moon in case of rocky planet, and here we do not see any moon at the later stage. So this red-orange color, it represents the entropy of the mantle material, that is the forsterite, and the iron core is in gray, but I do not find gray here clearly. So, and this is for the icy planet, and the disk vapor or mass fraction in case of this rocky planet is about 0.3. That is the rest 0.7 or 78% of the mass is in liquid phase. Therefore, the accretion of the material has occurred, and we can see a moon at the as an end product. But however, in case of icy planet case, this VMF is very high, and it's almost about 1. So, and for both these models, they have considered these fixed parameters. So here they are mentioned. So if we look at this picture, so this is for the rocky planet and the icy planet, and we can see that this is the gamma value, and this color bar, it explains that the higher mass for the impactor. So if we see the mass of the impactor increases, that is the mass of the accretionary disk, or the total mass of the accretionary disk, that also increases. So the disk mass, this is the MD is the disk mass, and this MT is the total mass of the whole system. And in this case, it is the momentum. So the momentum of the disk, and here is the total angular momentum. So both of them has been plotted against the total mass of the system, and it is normalized against the mass of the Earth. So and this color scale is based on the ratio between the impactor mass and the total mass. So here we can see that gradually with this kind of pattern is observed. And here what we can see is the larger mass. If the mass of the whole impactor is high, then the total amount of VMF or the vapor mass is higher, and it also increases with the velocity. So if the fractionally larger impactor, it contributes to a higher impact induced heating, and therefore the VMF amount will be also higher. And because the whole kinetic energy, if the kinetic energy and the heating of the system increases, then the amount of vapor phase will be higher, and therefore the VMF amount will be higher. So from this model, these are the general outputs that has been calculated, and this is for rocky planet, and the similar output has been found from the icy planet. So I am not very sure about the interpretation of these, but however, these color, they indicate the output from different model. For example, this blue line that indicates if the exponential model is taken. The green, in case of the green line, a polynomial disk model is taken, and the SPH simulation gives this dotted black colored curve. So here, what they have plotted is the ratio between the radial distance from the planet, and it has been normalized against the Earth radius. And they have plotted it on surface density, temperature, vapor mass fraction, and this is the pressure. So we can see that the vapor mass fraction, that does not have much change with the increase in the radial distance from the planet, and temperature also decrease very slowly. However, the surface density, that if we look at the SPH model, it has a sudden decrease, whereas in the other model the decrease is gradual. So the similar kind of model has been plotted for rocky planet as well. And if we see the vapor mass, in that case, the vapor mass is higher in case of the rocky planet, sorry, the icy planet compared to the rocky planet. Otherwise, these curves almost look a little similar to me. And here, what they have discussed is as a function of the radial distance normalized against the radius of the Earth, the surface, how the surface density changes, or surface density of the accretionary disk that changes with time. So we can see that gradually the surface density that flattens, and the density gradually decreases. However, we can see that the radius of the spread, it gradually increases with time. And also another thing is that this for the rocky planet, the total planetary the final disk mass is higher compared to the icy planet. So from output of this whole simulation, what they have found is that the VMF like concentration, it has a very important role to play based on which it is decided if the moon or moonlets that will be formed or not. So if in case of a moon forming disk with a high VMF, it is not capable of forming a moon that is very large with respect to size of the planet. And this study supports the canonical model, which has a lower amount of VMF, that is about 0.3. So therefore, canonical model is very will be able to form this Earth Moon kind of system. And also, if we look at this image, so this is for the silicate rock or the rocky planets, and this is for the icy planet, and this is the planetary mass. So and this planetary mass is normalized against the Earth mass. So this is the Earth's mass, and this color gradient, it shows that these orange color or the bright colored planets, they are able to form large moons. So here we can see that these planets, they have moons, whereas if this planetary mass exceeds a particular threshold limit, no moon can be formed. So this limit has been they have found this limit to be 1.6 R. So where R is the Earth's radius, so about 1.6 of the Earth's radius is the threshold till where moon can be formed. And if we convert it into mass, then this mass will be different. For example, about less than about 6 Earth's mass for rocky planets, whereas for icy planet it will be less than about 1 Earth's mass. So this model also discusses the limitations, or where they have not discussed much. That is, apart from this particular type of formation of the moon, this particular model, there are other models as well that they have not dealt with. So this model does not exclude formation of small moons around large planets. So they only mainly focus on formation of larger moons. So if when the disk cools down and the VMF amount decreases, the gas drag effect will also weaken, and small moonlets will start to form. So in these cases, like small moons can be formed, and this particular model does not deal with these kind of scenario. Other theories, they suggest that moon can be formed by gravitational capture as well, or okay, they can be formed within a circumplanetary disk, or in certain conditions, nearly intact impactor can also be captured due to the gravitational field as a moon. So this particular simulation, so they do not cover these kind of scenarios. Also, they mentioned that the limitations are, so they have used particular parameters. For example, impactor size or velocity, but there are different other parameters as well, which they have not considered. And they have taken n member scenarios where IC, only IC kind of impactor and the like the planet are interacting, or rocky planets are interacting. However, in a collision between icy and rocky planets is possible. In that case, the impactor contribute more to the moon composition. However, this is a very rare scenario because of the ice line, and generally rocky planets, they do not like the impactor of the rocky planets are generally similar in composition. So therefore, this kind of scenario is rare. And also the main outcome, or the conclusion from this study, what they have concluded is that this particular model predicts that moon forming disk, it needs to be initially liquid or solid rich, so that large size of larger moon can be formed. For example, in case of Earth moon system, so for particular this system, the initial moon forming disk, it needs to be liquid or solid rich. And this canonical model of moon formation is more fit in this particular scenario. And this model predicts that the planets whose radius is smaller than 1.6 of the radius of the Earth will be good candidates to host fractionally larger exomoons. And therefore, when we are looking at the like the Kepler or the Hubble telescope, so we should focus more on the planets which have a smaller radius. However, among the 54 planets that these instruments have looked till now, only 4 of them fall within this particular limit. So more focus should be on finding these kind of planets and looking for moon. And super Earth-like situation, or is like composition, is a better candidate than mini Neptune composition to host exomoons, because in this case they have, because they have lower mass, uh, and they have a higher hydrogen or helium gas contribution to the disk, and therefore the vapor contribution will be high, and there will be less chance to form larger moon. So that is all I had to say. So I do not have clear idea of the modeling part, and many of the parts are not very clear to me, but that is what I could make of the paper. Thank you.
Okay, thank you very much, Umi, for leading the paper. I think it's great. Actually, I try to learn from what you present. It's interesting. So do we have any immediate questions? I think, or unclear parts that could be raised so that we could learn together.
Right now, I don't think They had actually mentioned the limitations which I thought could be questions, like they have considered very less parameters and they have not considered the other kind of scenario, but they have already mentioned that those are the limitations of the model. So
Okay. By the way, for this outcome number one, so model predicts that the moon formed disk needs to be initially liquid or solid-rich. Okay, so you have to be vapor poor. I think that's
yeah,
what's
it should be like less vapor concentration. For example, in canonical model, about 70% is liquid or solid rich. So therefore, they say that this is a better fit. However, another from this canonical model, as they have already mentioned that it is difficult to explain the isotopic ratio, and they mention presence of other sources, for example, like some other, like similar kind of impacted composition or instantite chondrite type of composition. So like this drawbacks are also associated with this impact model as well.
So the question to the group, there's a parameter introduced called eta, and I think there's a typo in the paper because it was called the pressure graduate parameter. And then later in the caption is actually called the pressure gradient parameter. So I myself am not clear, but I'm gonna put this out there to the group. What do you believe is the controlling factor by eta? Like, what do you think, how does it affect these results? If it's a pressure gradient, what do you think the intuition is there for seeing how eta would affect the simulations? I'm guessing it might be related to the vapor drag, assuming, I guess I'm not sure what eta is referring to. Is it the pressure gradient of the vapor disk, or is it the pressure gradient of one of the bodies? I'm not quite sure. So if it's related to the pressure gradient of the disk, then that could affect the fall time. So I think, Urmi, if you go to the equation, that really complicated looking equation that she derived that one. Let's see. Okay, you can see eta is in there under tau f. So to the -1, so as eta increases, the stopping time should decrease. So the higher the pressure gradient, the faster the stopping time. So I guess that kind of describes how these moonlets would fall to the planet faster as the pressure gradient increases. So that might be one way to get some intuition on one of those later figures.
Is that also the drag effect here?
I think, yeah, I think it's related to the drag effect.
So what could naively say is positively correlated with the drag effect, with a higher pressure gradient value?
Yeah.
I think that's,
That's the most straightforward way to think about it. Yeah.
Yeah, although it's not linear or simple exponential relationship, I think it should be way more complicated.
Right. And I guess kind of related to that, does anyone have any good intuition on slide 9? You see how the simulation outputs are colored by entropy. What's the role of entropy here? I myself don't have a good intuition there.
I don't know. This is my guess. Is that do they also want to describe how well this impactor to the, let's say, to the, let's say, the impactor to the impactee. Maybe that's not a correct word to say that. Do they really want to say that how well is this two mixture goals and ends? Because to me, that let's say at the end of it, basically, they're trying to say, okay, maybe I'm wrong, because they started with low, right? Started with low entropy,
Yeah.
all of them. And at the end of, and when the simulation ends, then ends up with a very high entropy.
Yeah, I think there was a sentence in the paper that says these two simulations, Rocky Planet, Icy Planet, have the same mechanical results. Like you can essentially see just the shapes are the same at the end of the simulations, but thermomechanically they're very different. And it might be related to what you were just saying about the mixing.
I think we'll ask Nikki.
Yeah.
I think both of your questions are good questions to Nikki to illustrate to the audience. I listened to her talk before, and I'm always amazed by her videos.
The videos, yeah. Once
I
you
was
play
like,
the videos, it's it's hypnotizing.
Yeah, it looks like Hollywood movies. So
Yeah.
you play them. So that's really bizarre how this hydrodynamics simulation, particle simulation really goes.
Yeah.
But by intuition, so that probably that means from the beginning to the beginning. Actually, it's a little bit counterintuitive, right? So because we will think that it's more well mixed at the end of it, but it turns out to have a higher entropy. Because I think that end of it that should be
You know if she's ever mentioned anything about the probabilities of these different scenarios, whether the canonical hypothesis where you have a Earth-sized body being hit by a smaller Mars-sized body versus two equal-sized bodies colliding. You would think, if you think of the size distribution of objects in a solar system, it would have something like a power law. You would have fewer and fewer larger bodies and a bunch of smaller bodies. So I wonder if you can compute some sort of probabilities associated with like the canonical hypothesis. Is that, would you expect way more of those kinds of situations occurring versus two equally sized planets colliding?
at any angle.
Was that, hey, Jungjo, I don't know. Was that choppy? I didn't hear much of what you said. I don't know.
Because my internet connection is not stable, I think.
Oh,
Yeah.
okay. Okay.
So I said that the angle of the collision between the bodies also have a large consequence for the results. So it is not only the size of the two bodies matters, or relative size, but their angle when they hit against each other is very different. I think that's also one of the parameters that Miki put in the model. So I don't think he would follow a power law unless you are assuming that all collisions in the solar system all occur randomly.
Right. But they're all, I guess, in the protoplanetary disk, they're all have very similar angular momentums, well, at least similar angular angles, directions. So I would bet, yeah, like you're right. It's not a power law in terms of angles. I'm sure it's actually some kind of weird bimodal, trimodal distribution or something like that. I'm not sure. That's my intuition.
Yeah, that's my intuition too. I think yeah, we could throw this question to Miki on Wednesday to see what is her interpretation on this. Okay, any more thoughts from our participants today? Okay, if not, I think we could end our meeting today, and let's wait for Wednesday for Miki to give us the presentation and tell us the whole story. Okay, have a good evening, everyone. Bye-bye. And thank you, Wumi, for leading the discussion.
Thank you. See you all later.